In this video, we are going to discuss approximations, types of errors, and how these relate to the Taylor series. We need to discuss this because we need to determine the sources of error when performing numerical calculations. Let's dive directly to it. The first type we're going to discuss is the round-off error. This type of error is most easily the culprit when comparing between experimental and theoretical or analytical results. For example, it's always much easier to do the mathematics if we use 10 meters per second instead of 9.8 meters per second squared for the acceleration due to gravity. For y equals 1 half gt squared with t equals 3 seconds, then y equals 1 half times 10 meters per second squared times 3 seconds squared will give us 45 meters. Using 9.8 meters per second squared, then y equals 1 half times 9.8 meters per second squared times 3 seconds squared will give us 44.1 meter. The error is 2.04%. Of course, 2.404% is not so much, but if the measurement of time also has an error, then the height y will also increase in error. If the height y is used in a subsequent calculation in new variables, then that error will propagate throughout these new variables. This is called the propagation of errors. One small error at the beginning will lead to a larger and larger errors towards the end of the calculations. To discuss the second type of error, we'll review the Taylor series. Any function can be expressed in terms of the Taylor series. The equation is shown. X sub I is the ith element of the variable x. If we use numerical computing terms, x sub I is the ith element of the array x with 1 by n dimension. H is the interval or the difference between two adjacent elements of x. It is assumed that this interval is the same and thus evenly spaced. In some cases though, this interval is not necessarily the same for all values of the elements of x. In the use of the Taylor series, it is sometimes necessary to choose the number of terms that you are going to use. This may be due to the difficulty in taking the derivatives of the function by hand, difficulty in analytically solving a theoretical problem if we use higher order terms, sufficiency of a certain number of terms, or tolerance in the error. If you select only up to n terms in the Taylor series expansion, the sum of all the other terms beginning from the n plus 1th term becomes the error term. This term is called the truncation error, or simply the error. Truncation error is an error that results from using an approximation instead of an exact one. This term is specifically used in numerical computing. In general, a methodological error is introduced into the routine whenever a complex mathematical expression is replaced by an approximate or simpler one. This type of error is typically associated with errors arising from theory and comparing with experimental results. In the simple pendulum, the equation of motion is given by a differential equation of the form as shown. Using the small angle approximation means that we have to expand the sine theta term using Taylor series and actually select only the first term, that is, sine theta is approximately equal to theta. The reason for doing this is to be able to easily solve the differential equation by simple integration. So we replace sine theta by theta here, and this differential equation is easily solved. The sum of the succeeding terms beginning with the second term becomes a truncation error. One way to solve for the truncation error is by simply subtracting the approximate value from the actual value. In other words, sine theta minus theta. The fourth column, highlighted in yellow, is the truncation error. This truncation error increases with increasing angle, as you may have noticed. That's because you can no longer ignore the higher order terms. If we take a look at the first four terms of the Taylor series, we can see that the second term is already quite comparable with the first term and significant for angles above 15 degrees. If we go back to the error table, we can see that the error becomes greater than 1% from an angle of 15%. At this point, you may ask, what is a good or acceptable error? Is it 1%, 5%, or 10%? I would say that it would depend on the system. At the moment, we are talking about small angle approximation for the determination of the acceleration due to gravity. Let's take a look at and compare between two simulations, the one with the small angle approximation and the one that is numerically solved using MATLAB. The darker hue in both videos represent the small angle approximation, while the lighter hue, which is currently behind the darker hue, represents the numerical solution and thus can be considered as an exact solution. Let's play the video and take a very close look at their behaviors. You see that if the initial angles are less than 20 degrees, the variation between the small angle approximation, which is the black circle, and the numerically solved ODE, which is the light gray circle just behind it, is quite small even after several oscillations. On the other hand, if the initial angles are greater than 20 degrees, the difference can immediately be seen. The darker blue is computed from the small angle approximation, while the lighter blue is from the numerically solved ordinary differential equation. Thus, in this case, we have chosen the angle 20 degrees because we have compared between the two results. The links you need to further understand the discussions are found in the UPB VLE Physics 131 Week 1. Now that we understand errors better and how the Taylor series represents these errors, we can proceed with more computer programming. Let's talk about a few more functions that might be useful. The for loop is quite useful if you want to perform iterations, which is quite useful for series expansion. The syntax is quite simple. You begin with the for command, followed by the index with a range of values, which in this case is from 1 to n. In the next line, you will have your statements containing the commands that will be executed as long as the values remain within the index. Once the index has reached the maximum value, the for loop ends. You may also need to use the command hold, and it's used to retain the current plot and allow a new figure to be placed over the current plot. Let's take a closer look at how this works. So the first line clears all the variables, CLC clears the command console, and then this line tells MATLAB that n is a new variable and that new variable has a value of 10. We also define a new variable sum, which has a value of 0. Now what this for loop does is that it will iterate from the number 1 to this value n, which in this case we assign the value of 10. So this is from 1 to 10. By default, the interval or the step size is 1. So what's going to happen is that first it assigns I equal to 1. And then it will compute for the sum. Okay, so the sum is equal to sum plus I according to this line. What does this mean? Before this line, we have defined the sum to be 0. So this means that this parameter here or this variable here is 0. And since I is equal to 1, then 0 plus 1 will give us a new value for the sum. Okay, what this does is just it prints out the value in the command console because it doesn't have any semicolon. Okay, so now the new value for the sum here is 1. And then there's no more statement after this, so it goes back here, and now it creates or it assigns I a new value, which is 2. It executes this command. Okay, now since sum from here, sum is already 1, and since I is 2 here, so this is 2 and this is 1, then this new value for the sum will become 3. And then in the command console, you will see that this becomes 3. And then afterwards, goes back there, and then I is now assigned a new value, which is equal to 3. Okay, and then since this is 3 and this is currently 3, then this becomes 6. Okay, and then this displays the value 6 in the command console. Okay, and then the next is I equals 4, and then we have sum. So this is, since this is 6 and this is 4, then this becomes 10. Okay, and then it displays 10 in the command console, and so on and so forth. Okay, until we go to I equals 10, in which case the sum would have already been 45, and this will be 10, so this value will be 55. Okay, so now let's try to run this code and see what it looks like. Okay, so I click run. Okay, and then I go to the command window, and I see that in the first iteration for I equals 1, the sum is 1. For I equals 2, the sum is 3. For I equals 3, the sum is 6. For I equals 4, the sum is 10, as we have discussed. And for I equals 9, the sum is 45. I equals 10, the sum is 55. So that's what the for loop does for you. It avoids or it helps you by so that you don't have to write it in this way. What if I tell you, or I give you a problem that says you should add all the numbers from 1 to 1000? You don't want to do this method. What you want to do is to go back to your MATLAB script. You type here 100 to the which is the highest value for n, and then I click run, and then you see that the final sum is 5050. Okay, now here the interval is set to 1. You can define an interval which is less than 1 or even greater than 1 if you like so. So if we have an interval 2 here, then it will only add 1, 3, 5, 7, and 9. If we change this to 10, then it will only add 1, 3, 5, 7, and 9, which is 1 plus 3, 4, 4 plus 5 is 9, 9 plus 7 is 16, and 16 plus 9 is 25. So let's see if that works. See, sum is 25. I can change this to a smaller value, 0.1, and this will give us 500.5. Now I can choose to remove this if I don't want to display the values and just compute it so it doesn't display any value. Okay, I can choose to type sum here, okay, and get the number here. Or I can go to the workspace and see that the sum is equal to 500.5. Okay, or I can simply add sum here, and then it will immediately display the value of sum. Okay, so this is what you can do in MATLAB. This is what it looks like in Python. I naturally have to add this line because I need this command in order to define values from 1, 2, 3, 4, 5, 6, 7, 8 up to 9. So this is the reason why I have this line. So first I initialize, or I set the initial value of sum equal to 0. And then the for loop here, the syntax for the for loop here is like this. You write down the for loop, and then the index, and then the values of the index is written like this. For I equals in np.arrange 1 to 10. What does arrange do? So I press Command I here, then we see that arrange has a syntax of the first argument is start, the second argument is stop, and the third argument is step. If you see the square brackets here, it means that these are optional. So if I write only arrange, let's say arrange np.arrange 10, the default start value is 0, and then it will write down up to 9. Now notice that it doesn't include the value 10. So if I write it like this, 1 to 10, it starts from 1 and ends at 9. So 1 is included, but 10 is not included. Okay, but if I do it like this, so 2, and then I press enter, okay, we see that it skips every 2 units. Okay, so this is how you write the values of the index in the for loop in Python. Next, if you recall, in MATLAB, we wrote the sum as sum equals sum plus I. Okay, like this. I can just remove the hashtag. Okay, but in Python, you can also write it like this, if you wish, without the semicolon. But a simpler term or a simpler method is to write it like this: sum equals sum plus equals I. This means that this basically means the same as sum equals sum plus I. Okay. And of course, in Python, you really need to use the command print. Otherwise, the results will not be shown in the command console. So let's run this. Okay, and we see that the value is 45. Why is that? Again, because 10 is not included. So it only sums from 1 to 9, not from 1 to 10. If you want to include the value 10, we have to place here 11. Okay, now if you want to change the index or the step size, you can run it. So we have 595.003. Now why is that? Because now all values between 10 up to 10.9 are included. So I have to change this to 10.1 so that it only adds up to 10. Okay, so now I have the same result as in MATLAB 500.5. Okay, so it's a little bit tricky when it comes to Python. Okay, the next thing that we need to consider is creation of a function. In MATLAB, we can convert this. You can easily convert this to a function. The syntax for a function in MATLAB is like this: function, and then you have your output variables, and then the name of the function, and then the input variables, and then the statements within the function. Okay, so how do I change this to a function? First of all, I need to remove this. And the first line should write function, then sum, which is the output variable, equals summing up, and then the input variable, which is the minimum value, which is let's say min val, and then the maximum value, which is max val, and then the step size. Okay, so now we can remove that because n is actually the maximum value, and I'm going to write the maximum value here. So this is max val and the minimum value here, which is min val, and then the step here. Okay, now we have our function. Okay, so there's one thing that you need to know. Here I wrote the name of the function to be summing up. It has to be exactly the same name as the script. Otherwise, it will not work. So now that we have that function, I can write here now summing up 110 and the step size of 1, then it will give me 55. So I can call this function if it's in the same folder or if it's in the correct folder. It has to be, if you're going to call the function, you have to be in the correct folder where the function you're calling is located. Okay, so let's try another value. Summing up 1, 10, and then 0.1. Of course, we know that this will give us 500.5. In Python, this is what a function looks like. We use the command def and not the command function. So this defines a function. This is the name of the function. Notice that we didn't place the output value. Okay, the output value here is sum. We have the minimum value, the maximum value, and the step size. Okay, of course the sum is the initial, 0 is the initial value for the sum, and here is my for loop. Here are here are the values of the indices. The minimum value is my minimum, maximum value is maximum plus step. I added here the step because remember, the arrange does not include the last value. It excludes the last value. So if I want 10 to be included, for example, I have to add 10.1 so that 10.1 is not included, but 10 is included if the step size is 0.1. So this adds all the values, and this returns the parameter sum. Okay, so if I press the run button, then it will give me 500.5 as expected. So if I change this, for example, to 1, okay, then it will give me 55. Okay, and notice that compared to our range, if I put 10 here, then it adds up to 55. But if you use just a range here, if I use just a range here, it will just give us 45. And again, the reason for that is because I added this step size here in this value for the index. Okay, so if I change this to 0.1, then it should also give us 500.5. Of course, if you want, you can round that number up because it's too long. So, and if you do that, okay, so we have 500.5. Even if it's 2 decimal places here, since it's 0 there, Python just gets rid of the 0. So if I change this to 3, for example, we'll still print out 500.5 because there are just 3 zeros after the number 5. Okay, so these other functions, the whole, the xlim, and the grid, are for plotting. Right? I'll just leave it there, okay, so that when we go to the discussion for plotting, then we can come back to this and use them and see how they work. I'm also going to leave this out here because these are the equivalent in Python. Okay, now the yellow box corresponds to commands in MATLAB, while the green box corresponds to commands in Python. In general, any type of element-by-element multiplication of an array in MATLAB requires the dot operator just before the operation, except for addition and subtraction. For example, if I have a row matrix X, I can assign the variable Y to the individual sign values of X using the second line. So the output of this is sine of 1, sine of 2, sine of 3, sine of 4, sine of 5. So if this is a row matrix, this will also be a row matrix. Then I can multiply the array X with the array Y by doing the operation as shown, a dot before the operator. Okay, notice that the dot is placed just before the operation. And again, Z will have a row matrix with also 5 elements. In Python, you have to create an array, but before you can do that, you have to import numpy as np. To define X as a row matrix, you have to use two pairs of square brackets, and separate the elements with commas, as shown. We'll discuss how to create a column matrix when we are in week 3. To assign values for the variable y, you have to use the sign function in np and tell Python that X is an array by stating this command. Since Python already recognizes X as an array, then the values for the variable z is simply computed as x times y without the dot as compared to MATLAB. I hope you've learned a little bit more about computer programming. We will be using the Taylor series in our future discussions. You are now ready for Machine Problem 1. Please refer to the detailed instructions found in UPB VLE Physics 131 Week 1 module. I hope you perform in this machine problem and remember what we learned today about Taylor series. Next week, we'll talk about numerical differentiation and integration.